Hello. In section 5.2, we're going to continue what we were doing in 5.1, finding area between the graph of a function and the x-axis on some interval. In 5.1, we were approximating the area using rectangles. So we were saying, okay, let's find this area by constructing rectangles, finding the areas of the rectangles and using that as an approximation. Well, we're ultimately going to find the exact area, and the way we can do that is by using what we call a definite integral. Okay, and this is what it looks like. So we'll talk about what that means in just a minute, but the idea is a definite integral will give you the area, and we're talking the exact area. Okay, we'll give you the area between the graph of a function and the x-axis between two values. Okay, so in our last video in section 5.1, our very first example was to approximate, or we were looking at the area bounded by the graph of the function x squared on the interval from 2 to 6. If you remember that, we were finding that area. Okay, so if we are wanting that exact area, then we would say it's the definite integral from 2 to 6 of the function x squared. But we approximated it in 5.1. If we want the exact area, we would evaluate that definite integral to get the exact area. So we won't be able to evaluate that definite integral yet, but we will down the road. Okay, so let's talk about what all this stuff means. Okay, first of all, we have this squiggly black symbol, which is called the integral sign, and its shape is kind of like a super skinny S, because it stands for sum, because we're summing up the areas of the rectangles. So that's our integral symbol. The A and the B, the left side of the area where we're calculating, that left value is what we call our lower limit of integration. The right side of the area is the upper limit of integration. So that's what our A's and B's are. Inside the integral, you'll be giving the function that you're finding the area between the graph of between that graph of that function and the x-axis. That's called the integrand. Kind of like when you have radicals in algebra, radicals and what's underneath is called the radicand. Kind of that same terminology. That's the function that you use. You plug in your x values from A to B, whatever they are, into that function to find, remember, the heights of the rectangles. And then this last symbol out here, this dx, that's just what's called the differential. It's part of the notation. It goes along with the width of the rectangle if you're looking at the formal notation for the definite integral, which we don't really spend time on in this class. Now, the one thing to notice is the d, there's always going to be a d, but this variable x could be something else depending upon what the independent variable of your function is. Okay, but they must be the same. So this is no good if you see something like this. This is a bad problem if someone says, find the integral from 2 to 10 of the function 3x plus 5 squared dt. Okay, problem. Here in the function, my independent variable is x. This should be an x. So they always have to match. So you know, because what happens if you would go to other higher level calculus classes, you might be integrating in terms of one variable, but you have another variable. So it gets a little crazy. So you have to say, what are you integrating in terms of? Kind of like when we differentiate. Okay, so let's do some more approximating. Oh, but before we do, let's talk about this. So without calculation, what can you say about the relationship between the values of these two integrals? Okay, well, when I look at them, same lower and upper limits of integration. This one's e to the x squared dx, and this one's e to the t squared dt. So the only thing different is the independent variable. So it doesn't matter. It's just saying this graph, my horizontal axis is x, and this function here, e to the t squared dt, my horizontal axis is t. Exact same values. Your independent variable doesn't matter. So these will be exactly the same. They will be equal. Okay? So what does that tell me about this? Find the value of this integral minus this integral. Okay, so once again, same variable, or this one's in terms of x, this one's in terms of y. They're exactly the same otherwise. When I subtract, if I say this one was 15, this one would be 15, you're going to get 0. Okay, so just knowing that it doesn't matter what the independent variable is. Okay, now let's do an example. So here we're doing something that we did in section 5.1, but the directions are just different, but we're doing the same thing. So it's saying, this is like number 23 in your homework on page 248. It says estimate the definite integral from 0 to 3 of this function f using n equals 6, meaning 6 rectangles. Okay, so here I don't know the actual function, but I have the graph, and so I can use the graph to find my function values for my heights. So first thing we need to know is 6 rectangles. What's the width of each rectangle so we can choose our x values? So if you recall, delta x, the width, is b minus a over n. So our our a is 0, our b is 3. So we're going from 0 to 3. Okay, so my width is going to be 3 minus 0, and I'm going to divide it up into 6 rectangles, which comes out to be 1/2 or 0.5. Okay, so then what I need to do is come up with the x values so I can that across here. So I'm going to start with a. Oh shoot! I didn't realize those were connected. Darn it. Okay, here we go. Try this again. So I'm going to just write this here. This is 0. Okay, so we're going to start with 0. So my first value is 0, and then I'm going to add my delta x. So I'm going to add my 1/2 or my 0.5 probably, if you're putting it in your calculator. And you're going to continue until you get to 3, your b value. So 0 plus 0.5 is 0.5. And then you're going to keep adding. And the number of times you add delta x, or your width, is the number of rectangles you should have. Okay, so this becomes 1, this becomes 1.5, 2, 2.5, 3. So I have 1, 2, 3, 4, 5, 6 times I added 0.5. Okay, so that means then that I'm going to have, those are going to be my x values. Oh, whoops, I did a 1/2, sorry. Okay, so what I need to do then is I need to calculate, because I need to find out what is the y value, or the function value, for each of those. So I'm just going to have to estimate with my graph. This is the thing where you may not have exactly the same as the answers that Steve made or as the book, but it's just because we can't tell exactly. So at 0, the point on the curve is 4. At 1/2, it looks to me like it's 5. At 1, I'd say, I don't know, 6.8 maybe. So there, I see I have to just judgment call. At 1.5, it's looking like a little more than 7. So how about 7.2? At 2, I don't know, 6.5 maybe. At 2.5, it looks like we're at about, my line isn't drawn so great. I'd say 5.2. And at 3, about 3.1. So those are my estimates. Okay, so we will need those. Those are going to be used for our heights. So let's do the left sum. Okay, here we go. All right, so practice one more time doing the rectangles. Okay, so we're going to start at the left, so we're starting at 0. So on each of these 6 intervals, that's where we're going to draw the rectangle's height. So we're going to go up to the curve. That's where we draw the height. So where our left corner intersects, that is our y, or that is our height, the function value. Okay, so when I'm doing the left-hand approximation, then I know that, remember, it's base times height, or width times height. So the width of each rectangle is 0.5. So then I have to remember, sum up the heights at the left endpoints of each interval. So this is 0. So that first one's 4. Okay, the next one is 1/2. I go up here to the curve. That's where I draw the height. So to find the area of that rectangle, I use the height, which will be at 5. Okay, so you get the idea here that now at 1, I'm going to go up to the curve and over. At 1.5, I'm going to go up to the curve and over. 2, up to the curve and over. 2.5, up to the curve and over. It's kind of hard to do those. All right, so my left values will be 0, 1/2, 1, 1.5, 2, 2.5, and not 3 though, right? Because this is my left endpoint. Okay, but I do have 6 rectangles. So I use the first 6 values to come up with these areas. So that means I'm starting here and I'm going the first 6 up to 2.5. So you're not using all of them. Okay. All right, so let's do this. Okay, so this comes out to be, my left-hand sum comes out to be 17.35 for the area. Okay, so let's do the right. And basically, where are we starting? We're starting at my first interval on the right. Here is the 1/2 or the 0.5. Okay, so that's where I go up and then draw the rectangle. So it's where the right corner intersects. Okay, so then basically I'm going to calculate the area of all those rectangles. So I know the width is going to be 1/2. So I just need those heights. So if I'm doing this, then my first value is the right here of this first interval is 1/2. So that's where I'm starting up here in my table. Okay, so my first height is 5. So I'm going to say 5 plus 6.8. So now for these, I'm using these values. Oops, that was the same color. I hate that. Let's don't do that. Now I totally have my color switched. Sorry. Wasn't my plan. Maybe if I try this. Let's see how that looks. Okay, here's the right hand. Okay. All right, so I add up those 6 values. Let's make sure I have 6. 1, 2, 3, 4, 5, 6. Okay, so the right hand comes out to be 16.9. Now let's double check that for a minute. Which one is the bigger one? Okay, which one overestimates? This one, we can't just look at it. It's hard to tell without seeing the numbers, because what's different about my function than the ones we saw in 5.2 or talked about was this one's increasing and then it's decreasing. So these rectangles over here, I'm missing some stuff. And then over here, it's hanging over. Okay, same kind of situation down here. So when your function's increasing and decreasing, then we just have to go with these numbers. We can't really predict which one's over or under estimate. Okay, but our best estimate, right, our best guess is the average of those two. So 17.35 plus 16.9 divided by 2. Should come out to be 17.125. Okay, so let's just kind of summarize that for a minute. So if I'm going to say that the integral from 0 to 3 of f of x dx, we're going to say it's approximately 17.125. Okay, now I did use my not really a calculator, I used a computer program. The exact area or the exact value is, oh no, sorry, I couldn't use it on this one. Duh. I couldn't because I don't know the function. Okay, all right. So here we go. Here's one where we're not going to actually draw the rectangles. Now, the only thing tricky about a lot of these in your homework is it's just number crunching on your calculator, and it's a little tedious. Okay, so if I want to approximate this definite integral, notice how my variable is w now. Totally fine, same deal, but they match. Okay, so we're going from a equals -2 to b equals 7, okay? And this is the natural log of w plus 4. That's my function. So that's what I'm going to use to find my heights for each of my w's, okay? So let's talk about the width. The width is delta w. What's the change in w, the horizontal change? So that's going to be my b, which is 7, minus my a, which is -2. So this one's a little tricky because you're subtracting a negative, so be careful. Divided by n, which is 3. So I have this width that I'm finding the area is 9. Dividing it up into 3, that gives me 3. So I have 3 rectangles, each with a width of 3. Okay, so I start here at A equals -2, and then that's what I'm adding. I'm adding 3, my width, to get these x values. So I start at -2, I add 3, I get 1, I add 3, I get 4, I add 3, I get 7. Okay, so those are the x values I used to find the heights. So what did I do? I took this value and I plugged it into this function. So I had to use my natural log button. I had to take -2, add 4, and take the natural log. So these values I got on the calculator. You can stop the video and check them. I rounded to 3 decimal places. Seems like that would be pretty good. Okay, so let's find our left-hand sum and our right-hand sum. So my width is 3, and then I sum up the areas, or sum up the heights. So if I'm doing left, then I'm going to start with the first one. Okay, and then I'm going to use how many heights? 3, because I have 3 rectangles. Okay, so then I'm going to add those up. All right, so we're going to add those, multiply by 3, and get a left sum of, let me find my numbers, 13.143. Okay, so when I do the right, then I still have a width of 3, and now I start with the second value, second function value, that's my height, and I add those values up. So you should have as many heights as you have rectangles. All right, which gives me 18.258. Okay, so here's what we're saying then. We're saying that this integral from -2 to 7 of the natural log of w plus 4 is approximately whatever the average of those two is. So we'd add them together and average approximately 15.7. Okay, this is where I used the computer program to do the crunching. That exact value is actually 15. This is rounded, so I won't put approximately. I mean, it would have to round, so I'm just going to do it this way. All right, so exact is that decimal, okay, that it does keep going. All right, cool. So exciting stuff down the road. We'll be able to do exact of a lot of functions, not every function, but a lot of them. Okay, so 2 things here. In 5.1, this is what we were saying. Find the area between the graph of some function and the x-axis between 2 values. Okay, so that means basically find this area of this region. Okay, and so that's what we did. Now, in section 5.2, we're saying evaluate this definite integral from 0 to 5, the function 4x plus 4/5 x plus 2 dx. Okay, these are the exact same thing. Okay, same thing. Find this area. Okay, so same, they're just different notation. Okay, and so what we were doing in 5.1 a little bit ago is we were approximating area under a curve. But this here, my function is linear. I don't need to use rectangles to approximate it because I can find the exact value of that region using geometry. Rectangles, squares, triangles. Okay, so if the function's linear, you can find the exact area without having to use a rectangle approximation. So we're just going to divide it up into regions. So I can divide this up into, I see I have a triangle here, right? So I could say the area of the triangle. Then, how do you find the area of a triangle? 1/2 base times height. So my base could be this side here, which would be 5. And the height would be this side here, which would be from 2 to 6 is 4. So the area of the triangle is 10. All right, so then we can use this region here as a rectangle. Area of the rectangle is base, width times height, sorry. Or base times height, whatever. Area of my rectangle then is 5 by 2, which happens to be 10. All right, so the area of this region is, the exact area is 20, which means that integral 0 to 5 of 4/5 x plus 2 dx is exactly 20. Okay? So it may not be that the function's linear, but it's made up of linear segments. For example, in this graph here, this function. So if we want to evaluate the integral from 1 to 6, means the area between that function and the x-axis on this interval from 1 to 6. So basically, we're talking this region here, okay? So, well, we could just divide it up and kind of count squares, actually, all right? So I know that if I talk about this area, I've got 2 squares. Okay. And then these little triangles here, it doesn't matter how you do it, but they're each 1/2, half a square. Okay, and then here's another 1/2. Then we could say here's 1, and here would be 4, this region. Okay, so if I add those up, I got 2, 3, 7 and a half, 8 and a half. So we could say here the exact area is 8 and a half. That is exact. Okay, so those are the different ways that we will be finding areas. Sometimes exact, sometimes approximating. Down the road, we should be able to find exact with curves.